Okay, here in lecture 16, we're going to take a look at something called exception handling, which is the C++ mechanism that tries and almost succeeds in dealing with the problem of errors discovered while programs are executing. So you call a function, and the code in this function is executing, and along the way it discovers some kind of error. You've got a divide by zero problem, you've got a bad subscript problem, you're trying to allocate memory that's not available, you try to access a file that doesn't exist. What is this function supposed to do now that it's discovered this error? Well, in traditional languages that don't provide something like exception handling, there are about 5 different techniques that are used. Maybe the most common one is to return some kind of error value. For example, if you have a set of int and you do a find of, let's say, 27 in the set, if that 27 is not found, that is, the find member function fails, we know that find returns the .end iterator for the set, which is a special value indicating an error, that is, indicating that we could not find the value. Another approach that's much less common is to require the user to pass in a pointer to some kind of error parameter or a reference to some kind of error parameter that the function will fill in with some value if it discovers some error. Yet another approach is to use a global variable. This is actually done by some older library routines, and set that global variable to some kind of error value if the function fails for some reason. Now, of these 3, returning an error value often works, but it can't always be used. For example, if you're computing the log of some value, that log function is returning some approximation of a real number, and any real number is a valid log of some value. So returning some kind of special error value in that case just doesn't make sense. Math functions like log, exponent, sine, cosine, square root are so commonly used that it would be unreasonable to expect a programmer to provide an additional error parameter that they had to check every single time they called a math function. Assigning a value to a global variable is not a great idea because programmers frequently forget to look at the value of the global variable after they call a function. Or for that matter, they forget to set the global variable to a clear state before they call a function. So another couple of, quote, techniques, unquote, are you can display an error message and just keep limping along until some catastrophic problem occurs, or you can simply give up and crash or exit from the program. So all of these techniques are used. None of them is particularly wonderful. And the general problem with all of these approaches is that the calling function, or the calling object, is at the conceptual level in the program where we can make a decision about what to do if something goes wrong, but the called function is the function that discovers that something is wrong. So we have this mismatch between where we have some idea what we would like to do about a problem and where it is that we detect that a problem exists. And this is why in C++ and other languages, the notion of exceptions was introduced, so that if a function detects an error, the function can do what's called throwing an exception back to whatever called the error detecting function. And then the caller of the error detecting function can catch, if it wishes, these thrown exceptions and can in some way handle the error that occurred. We already know about 2 kinds of errors that will crash our program. One is if we attempt to ask for a chunk of memory and that attempt can't be granted. For example, here we have an array of 1,000 pointers to long doubles, and we're going through each of the elements in that array and storing into that element the address of a new long double array of 1 billion elements. Well, a single long double is 16 bytes, so here we're allocating 16 gigabytes with every use of new, and for sure that's going to fail, very likely the first time through the loop. Another situation where we know our program is going to crash is if we have a vector or a dec in which we're able to do subscripting using an integer index between 0 and 1 minus the size of the container. When we use the at member function and give an index that's outside the bounds of the container, we know that will throw an exception and that will crash the program. Okay, so these are two different kinds of the so-called standard exceptions. If you attempt to allocate memory with new and new cannot get you the memory that you've asked for, new will throw what's called a bad alloc, that is a bad memory allocation exception. On the other hand, the at member function in a container, if you access an element that's outside the range of subscripts for that vector or dec, that throws what's called an out-of-range exception. It turns out that these standard exceptions are organized into a hierarchy. Standard exceptions are actually classes, and throwing an exception involves creating and throwing an object of a particular exception class. These standard exceptions have as their basemost class a class named exception. All right, so a bad alloc is a kind of exception. An out of range is a kind of exception. It would be awfully handy if all of these standard exceptions were described in the same header, but unfortunately the headers for these different kinds of exceptions tend to be sort of scattered around. Bad alloc is described in the new header. Out of range is described in the standard except header, and exception itself is described in the exception header. So let's take a look at how we could use this in actual code. Here on slide 5, we have what's called a try block, meaning that we're going to try to execute a sequence of statements. We have a suspicion that one or more of those statements might fail and throw an exception. So following the try block, we have a series of catch clauses. Okay, so a try block consists literally of the word try, and then an open curly brace, followed by a sequence of statements, followed by a closing curly brace. And what that means is we are going to try to execute these statements. We are hoping that these statements will all succeed, but it's possible that one of them will fail and throw an exception. So if an exception gets thrown by something within the try block, we have a sequence of catch blocks set up, and this is organized from most derived to least derived kind of exception in much the same way that we did with dynamic casts. We had CEO at the top, then manager, then employee. So here, bad alloc is one kind of exception that we might catch if new fails within that try block, or out of range is an exception that we might catch if we use the .at member function to access an element that's not within range in a vector or a dec, and there are various other things that might throw out of ranges as well. Now, if the exception was not bad alloc and was not out of range, then if it is a standard exception, it will be caught by this third catch block where we're looking for just plain old exception. And then finally, if the exception that occurred was not even a standard kind of exception, as your very last catch block, you can use the 3 symbol. And if you use the 3 dots, that should always be the very last catch in your sequence of catch clauses associated with a particular try block. Now, notice in the try block that if a particular identifiable kind of exception occurs, and if that exception is a bad alloc, then we will get a reference to the particular bad alloc object in this parameter named E, and we can access the internals of E to try to figure out exactly what went wrong. Likewise, if an out of range occurred, the out of range exception will be available to us through this reference E, and we can try to figure out why the out of range occurred, and so forth. I don't mean to imply that there's anything special about this name E. That's just the name that I happen to choose for the parameter for the catch block. But of course you could choose some name other than E. Slide 6 repeats things that I've said as we discussed slide 5. the catch blocks are examined in order from top to bottom, and the first one that matches is executed. Any trailing ones are then skipped over. And then following the sequence of catch blocks, whether one is executed or not, execution simply continues with whatever the next statement is following all of the catch blocks. Okay, so here on slides 7 and 8, we have a small program illustrating these two problems that we've just talked about, namely the bad ALEC problem or the out of range problem. We've included new and we've included standard except so that we know about the bad ALEC class and the out of range class. Those are the two kinds of exceptions that we're looking for. Okay, so in main, we have a for loop that's going to go for 1,000 iterations, and inside the for loop we have a try block. The try block starts just as we enter the for loop for the current iteration, and the try block ends at this point here on slide 8, and we have two catch blocks following the try block, and below the catch blocks we have a cout statement and the curly brace that concludes the for loop. Alright, so let's see what this program is doing here. So for the first time through the loop, we're going to try this switch statement. Switch is going to invoke the rand function. We're going to get the remainder after division by 5. So that means we're going to have some value, 0, 1, 2, 3, or 4, within the switch. If the value happens to be 0, which ought to occur approximately 1 time out of 5, then we're going to attempt to allocate 1,000 arrays of a billion long doubles. And that is simply not going to work. That's going to throw a bad ALEC exception. So we pop out of the switch as a consequence of that throw. And here is the catch block that is waiting to see whether a bad ALEC exception occurred. Sure enough, it did. And so if we get a bad ALEC, rather than crashing, the program is simply going to display this message, caught bad ALEC. And then we will display this cout message, we are here, I is 0. And we'll go back to the second iteration through the loop. Okay, so in the second iteration of the loop, we pull another rand value between 0 and 4. Let's suppose this time the value happens to be 1. Here's case 1 at the top of slide 8. We have a vector containing 5 values, and notice that we're going to use at with a random index here between 0 and 5. Now, very roughly speaking, we're going to get a uniform distribution of values between 0 and 5 from this calculation, and that means that 5 times out of 6, if we have an index between 0 and 4, v.at of the index will be fine. We'll simply display the value at that index. Then we'll come down below the catch blocks and we'll say we are here, I is whatever it is, and we'll go back up to the next iteration of the loop. Now, unfortunately, approximately 1 time out of 6, we're going to end up here with an index of 5, and of course an index of 5 is out of range, and that's going to throw an out of range error. We'll find ourselves in this catch block, and we'll display the message caught out of range. Because we have this catch block, the program does not crash. We say we are here, I is whatever it is, and we go back to the for loop. So the for loop is going to run 1,000 times. We have two possible exceptions that can occur, namely a bad ALEC or an out of range. And because we have catch blocks set up for both of those, this program never crashes, but it probably will spew out these caught bad ALEC and caught out of range messages on a fairly regular basis. In fact, here's the output of one test run on slide 9. In fact, this is just the first 14 times through the loop. And of course, if you run this program, it may behave differently for you depending on which value your rand function starts with. Okay, so the first time through the loop in this example, no exception occurred. We got through the try block without generating an exception. That means we just fall through the catch blocks, and we get to the cout statement, which simply displays we are here, I is 0. The second time through the for loop, apparently in the switch, we got a case 1, which means that we're in this vector accessing part of the code. And also, we were unlucky enough to draw an index of 5, which is out of range, and so the @ threw an exception, and we come down here to display caught out of range. After we display caught out of range, we drop down to the black cout statement, and we display we are here, I is 1. Now, generating out of range, and therefore catching out of range, is a rare event. We only get into the vector code once in every 5 iterations through the loop, and even when we're in the vector code, we only throw an exception 1 time out of 6. So roughly speaking, 1 time out of 30 through the for loop, we should generate and catch an out of range exception. Okay, the 3rd time through the for loop, we don't cause any exception. We just get told we are here, I is 2. The 4th time through, the same thing. The 5th time through, in the switch expression, we evidently get a 0. And so this generates a bad alloc exception. That gets caught in the first catch block, and we display caught bad alloc. And after we've displayed caught bad alloc, we fall down to the black cout statement, and we display we are here, I is 4. Okay, so remember that i's value is always 1 behind the actual iteration through the loop. So we just finished the 5th iteration through the loop. Now, in the 6th iteration through the loop, apparently rand mod 5 is a 1, so we come down into this vector code, and in the @ function call, rand mod 6 is apparently 1, because v.at1 is this 2, and it's that 2 that's being displayed here. So we have a successful access of one of the vector elements in this case. There's no exception displayed, and we come down to the black cout, which tells us we are here, I is 5. And this continues in the same vein. Apparently we access the vector twice more successfully. We see another blue 5, and we are here, I is 6. We see yet another blue 5, we are here, I is 7, and so on and so forth. And this continues for 1,000 iterations. Now, when an exception occurs, we would certainly like to know a little more than that it was a bad alloc exception or that it was an out of range exception. One way we can find out a little more about what occurred is through the use of the what member function that's provided as a virtual function in the exception base class. So the what member function returns a C-style string. That is, it returns a pointer to the first char in a sequence of chars terminated with a null char. And the derived exception classes, such as bad alloc and out of range, provide overrides for what that give messages that make sense for that particular kind of exception. Now, when I say they make sense, I don't mean they're necessarily really easy to read. For example, here we have a try block. We are creating v as a vector of int initialized with 3 elements, and we're saying v.at7, which of course is out of range. So that's going to throw an out of range exception. Immediately below the try block we have our catch exception, and that out of range exception we're going to be able to access through this reference parameter e. We can invoke e.what to find out more details about this particular out of range, and what we get, at least on my system using GNU C++, is in the vector class mRangeCheck, that is, we're checking the subscript, and the subscript is 7, and that's greater than or equal to the size of the vector, which is 3. So in a nutshell, that tells us that we tried to use an index of 7 in a vector that only contained 3 elements. This is nice. It tells us what the problem was. Unfortunately, it doesn't tell us anything about where the problem occurred, so there's more information that we would also like. C++ provides several predefined macros created with the #define directive that will give us more information about where in the file we are and also what day and time the file was compiled. All of these predefined macros have names that begin and end with double underscore. So for example, underscore underscore file in all caps underscore underscore will be the name of the source code file containing this particular code. Underscore underscore line in all caps underscore underscore is the particular line number in the file. Here on slide 13, we've expanded our code example. Let's suppose that this is in a code file named ex1.cpp, so that when this out of range error is generated by calling the @member function with a bad subscript, the out of range exception is caught in this catch block, and we can display in file and the file name ex1.cpp @line, whatever this line number is in the file, in function, whatever function we're currently in, compiled on this particular date at this particular time, we have what happened. Now notice this reports when the program was compiled, not when this code was executed and this exception was thrown. Also, another problem here is that I'm being told where the exception was caught, not where the exception was thrown. So it's better than nothing, but still not quite what we're after. Here's the output that I would see. In file ex1.cpp @line 128, assuming this was line 128, in the function abc, blah, blah, blah. Okay, so we've taken a look now at situations that generate exceptions, such as trying to allocate too much memory or using the @member function with a bad subscript. And we've seen how to catch these exceptions. We haven't talked yet about how you can throw exceptions yourself. You can throw an exception by using the throw keyword followed by an exception object. Now, that exception object can be of any data type at all, even something really simple like an int. When you throw this exception, your program will do what's called unwinding the stack, searching upward and upward in the function call hierarchy until a matching catch block is found that's waiting for your type of exception. And if there's no catch block that's waiting for your type of exception higher up in the function call hierarchy, then the program will crash. Okay, so here on slide 16, we have some code illustrating a couple of different kinds of throws. We've got v as our vector of int containing 4 elements. I'm going to randomly choose an index between 0 and 7. And if the index is bogus, that is, if it's greater than or equal to the size of the vector, then if the index is an odd number, that is, if index mod 2 is 1, I'm going to throw a string. Okay, that is, I'm going to throw a pointer to a char. Otherwise, I'm going to throw an int, specifically the index. Now, on the other hand, if idx was less than v.size, I'll drop down here to this cout statement and say v sub, whatever the index is whatever the value at that index is. So, for example, v sub 0 is 2, or v sub 1 is 4, or what have you. In the remaining part of this code on slide 17, I have a couple of catch blocks set up below the try block, the first of which will catch a thrown string, that is, a thrown pointer to char, and simply display whatever that message is. The second of which will catch a reference to an int and print out a message saying bad subscript and whatever the int is. Here on slide 18, I have a few test executions of this little program containing this try block with these 2 throws and these 2 catches. The $sign symbol here is the Linux prompt, or the Unix prompt, or the Cygwin prompt. You can install Cygwin on Windows. Cygwin provides a Linux-like command line environment with a bash shell and the whole collection of Unix/Linux commands. To execute an application in Cygwin or Linux, you specify the directory where that program is contained. Dot means the current directory, and slash is the directory separator. So ./ex2 is how on a Linux or Cygwin system I would execute the ex2 executable program file that's in my current directory. Okay, so I do this once and I don't have an error. I get told that v sub 3 is 8. I execute it again and I get apparently a bogus even-numbered subscript generated. That throws an int, as you may recall. Let's take a look back on slide 16. All right, so if I get a bogus even-numbered index, that throws the int. The int is caught here on slide 17, and I display the message bad subscript and whatever the value is. So I get told bad subscript 6. The third time I run ex2, I get a good subscript. I get a 2 as my subscript, and I get told that v sub 2 is a 6. And then the fourth time, I apparently get a bad odd-numbered subscript. And so we throw this message, bogus odd IDX. That gets caught by this catch block, and it's simply displayed. Okay? Okay, so the bottom line here is that an exception is an object of some type. And you can throw any object of any type, and that either will match up with a catch block higher up in the function call hierarchy, or it won't, in which case your program will crash. Now, because an exception is simply an object of some type, it's very easy to define your own exception class or classes if you wish. In fact, an exception class does not even have to have any members within it. Here we have an exception class. The name of this class is bad thing. It has no members. The compiler will automatically give you a default constructor for this thing that does nothing. And over here on slide 20, we have an illustration of how we might use this bad thing exception class. We've defined the class in our code above the place where we want to use the class. And here in this try block, we're once again selecting a random index between 0 and 7. So half the time our index is going to be outside the bounds of this vector. And if we discover that the index is bogus, we can say throw a bad thing. Now, bad thing is a data type, but bad thing with 2 parentheses after it, that is how you invoke the default constructor to build a bad thing object. What's maybe a little weird about this is that this bad thing object doesn't actually occupy any space. But it is nevertheless a bad thing object, and consequently you can have a catch block set up looking for a bad thing. In this case, since the bad thing does not contain any information at all, you don't even need to specify a parameter name. But when a bad thing is thrown, this catch will catch it, and we can display to the screen that we caught a bad thing. Here on slide 21 are some example executions of this little program in a file called ex3.cpp. Again, we're executing this in a command line oriented Linux environment. By the way, if you did this in a Windows environment, the only difference would be that you would have like a C and a greater than symbol here to indicate your prompt. And you probably wouldn't need to type the directory name. You could just say ex3.exe to execute that program. And the behavior other than that would be the same. Alright, so here we're executing ex3, and apparently this first time we're getting an index of 3, which is within range, so we get told that the value of ex sub 3 is 8. We execute ex3 again. This time we get a bogus index, and we throw a bad thing object, we catch it, and we display that we caught a bad thing. We run it again, and we get a valid index. We run it a fourth time, and we get another bogus index and display that we caught a bad thing. Okay, so for simple cases where you simply want to know, did something go wrong or not, you can trivially create an exception class containing no members, and then you can construct and throw one by giving the class name in the parentheses, and in your catch block you can set up to receive a reference to this bad thing, even though the bad thing doesn't contain any data. Now, when you can, rather than just creating an exception class from scratch, it's a better idea if you can derive an exception class from a standard exception class. That allows you for example, to use the what function that is part of the standard exception class hierarchy. Also, it increases the probability that your exception will be caught somewhere. Even if somebody writes code not being aware of your exact exception type, they'll very likely have a catch set up to receive, some standard exception or some out-of-range exception or what have you. And if you've derived from out of range, then your exception will get caught. Now, in order to make use of the what facility, it turns out that all standard exceptions have a constructor where you can specify a string, and then that will be displayed by the what function if the user queries what in their catch block. So here is a new and improved bad index. Well, previously we had just plain old bad thing, which didn't have any data members or member functions, any constructor, anything useful. This time we're defining bad index, which is a variation on the out of index standard the out of index sorry. Okay, so bad index is a variation on the out of range standard exception. Now, I didn't use the word public here, and so that might concern you, but we're defining bad index as a struct, and what that means is that everything in the struct is public by default, including the base class that we're deriving bad index from. So struct bad index colon out of range behaves exactly the same way as if I had said class bad index colon public out of range. And then I would have had to declare the constructor here as public. Okay, so by using struct, I don't need to worry about using the public keyword because everything is public. Now this time, bad index, instead of being empty, does have a constructor, and the constructor simply receives a string as an argument and turns around and passes that down to the out-of-range base class so that the out-of-range base class can initialize the string value that will be displayed by what. Okay, and then here is code in this file ex4.cpp making use of the bad index exception type. Let me actually show you and execute this code here. Okay, so here is ex4.cpp. We have a whole bunch of headers at the beginning. And then here we have our bad index structure being defined. In main, I'm setting the random seed to be based on whatever the current time is. So each time I run this program, the random seed will be initialized to some different value, at least if I wait a second or two between executions. Then in my try block, okay, I'm going to declare v as a vector of int containing 4 values, and then I'm going to randomly select an index which is going to be some value between 0 and 7. If the index is greater than or equal to, I should say, the size of the vector, then I'm going to create, by using this oStringStream object, a meaningful string that describes what the error is and where the error occurred. All right, I'm going to use my underscore underscore file underscore underscore and underscore underscore line underscore underscore, as well as the specific index value and the size of the vector. And I will then turn around and pass that as a string down to the bad index constructor when I create the bad index object.
And the bad index constructor turns around and passes that to the out of range base class. All right, so because a bad index is a kind of out of range, if I check for and catch a reference to an out of range, I can then display the what message from within that out of range object, and a bad index will be caught by that catch. All right, because a bad index is a kind of out of range, so catching an out of range will also catch a bad index. Let's take a look at compiling this thing. So this is EX4. And this and all the other examples in this chapter are in the Lecture 28 example code files directory. And I'll run it. Okay. All right, so the first time I ran it, the random index that I received was in range, and so I simply got the value 8. Let me scoot. Here's the code. Okay, so the random index that I got must have been a 3, and so I'm simply displaying v sub 3, which is the 8. If I run the program again, this time the random index that was generated was a 7, and this message telling me the name of the file, ex4.cpp, the line number, line 27, where this error occurred, and the fact that the index 7 is greater than or equal to the size of the vector, which is 4. All right, so I get this very meaningful message from this exception about where the error occurred. And then each time I run this, I'll get some different result. This time I got a random index of 4. And although there are 4 values in the vector, the last one is the sub 3 value. And this time I apparently got a random index of 0, which worked, and so on. Okay. All right, so here on slide 25 are some other examples of, what might be produced when we test this program. Now, sometimes you might catch an exception at a certain level in your program where you don't really know how to handle that particular exception. And so in this case, it's sort of like hot potato. Well, if you're familiar with hot potato. So the idea of hot potato is that someone throws you a hot potato and you throw it immediately to someone else so your hands don't get burned. All right, so whoops, I must have hit the down arrow by accident in my chuckling there. All right, so if you receive an exception that you don't know what to do with, you can just rethrow the exception by just using the statement throw all by itself. All right, so if at a certain point in your code you catch an out of range error, but at this point in your code you don't know what to do about the out of range error, you can just say throw, and that will go up to the next higher level, looking for another catch clause that handles out of range. So, all right, so that gets us to the conclusion of exceptions. Some people try to use exceptions as a sort of general programming technique, and this can rapidly lead to, well, I have intentionally not mentioned the goto statement, because the goto statement is notorious to enable people to create what's called spaghetti code. That is, you can have a long function that has a bunch of gotos and a bunch of goto labels in it, and it basically is impossible to follow the logic of such a function, or at least it's extraordinarily difficult. So one rule is to just not use goto. Now, the problem with throw is, although it's a very powerful mechanism, not only are you jumping from place to place within a function, but throw actually enables you to jump across functions from a lower level function to a higher level function that eventually called that lower level function. And so whereas goto lets you create spaghetti code, throw allows you to create what I call spaghetti hierarchies, where it really is truly impossible to keep track in a meaningful way of where your code is coming from or going to. So exceptions are great. They do allow you to handle things that would otherwise kill your program, but you should use these only for error handling and not for, not as some kind of general coding mechanism. And you should try to isolate the throw to be just one or two levels below the catch that is waiting to receive that exception. Alrighty, so that is exceptions.